So, okay, this is written homework 11. It's all about diffusion, random walk, stuff like that. It's kind of a continuation in terms of like the concepts you guys learned previously with like statistics and probability, but now it's taking it a little bit further with like particle motion and whatnot. So this is more specific than just the probability that you guys did last week. So we have problem 1 here. It says random motion of 100 particles. So a scientist is measuring the random motion of 100 small particles in a long, very thin tube. With the aid of time-lapse photography, she locates all the particles at a given time. And again, 20 seconds later, she measures the displacements, all in the plus or minus x direction, and counts the number of particles that travel different distances from their starting points. Motion in one direction is arbitrarily called negative, and in the opposite direction is positive. Following table is obtained. All right, so this is really similar to that first problem that we had from last week where you have the probabilities and their respective displacements. So traveling, negative 10 micrometers has a probability of 0.23, for example. So this first problem is asking us for part A. It's most likely to find a particle at the original position, displacement of 0. It is also just as likely to find a particle at some positive displacement as at the same negative displacement. Probability symmetric around 0 displacement. So what this basically means is that everything is centered around 0, right? And whether you go positive or you go negative, the probabilities are symmetrical, right? So as you can see here, probability you move 10 micrometers is 0.23, and negative 10 micrometers, it's also 0.23. Same goes for 20 micrometers, 30, and negative 20, negative 30. They all have the same probabilities. It's symmetric, so it kind of has this, like, if you were to kind of graph it out, right, it would kind of look like this, sort of, right? Something like that. So it's just all symmetric. The motion of a single particle is very similar to a 1D random walk. Use this to explain why these two features of the probability table make sense. So we know the concept of random walk, right, is where you have like your steps left or right are generally going to be equal probability. So they have an equal probability of occurring whether you go left or right. And so the step of one molecule shouldn't be affected by any other molecule. They're completely independent of each other, right? So moving negative x or positive x would have an equal probability of occurring. And that's why your distribution essentially mirrors itself. So if we can draw kind of like a line right here, like I said, these are going to be the same, producing kind of like a bell curve that I was talking about before with the graph. And so, over a long period of time or multiple time steps, right, the average position of the particles is back where they started at, which is 0, which is why the probability of finding a particle at 0 is highest. So there's a couple different like aspects to the whole relating this table to random walk. So number 1, I think, is the easiest, is the fact that this table has highest probability at 0 micrometers, right? So that kind of matches up with the 1D random walk like characteristics, right? Because the average position, the average final position that is back where they started, right? So it's back where they started at 0 micrometers. So that's one aspect that kind of relates to why we can kind of assume that these data values kind of resemble a 1D random walk, right? And the second aspect, obviously, is the mirroring of the values, right? So, like I said, with a simple random walk model, you have the probability of moving left or right. Left or right probability is equal. So the step of one molecule is not affected by any other molecule, right? They're completely independent. So moving in the negative or positive x direction would have an equal probability of occurring, and that's why they kind of mirror each other. So these are your 2 points essentially as to why this table or a table of data values can be kind of related to a 1D random walk. Number one is because the highest probability is back where they started, which is characteristic of a random walk. And then the fact that your movement left or right has an equal probability. So it's that symmetry, right, around that like the central axis, right, around that original position. So those are the two features of the probability table that would kind of relate to a 1D random walk. Does that make sense to everybody? So average final position is 0, and then left or right probabilities are equal. Because it's kind of like flipping a coin, right? Heads or tails are equal. Processes are independent. So the fact that these values are mirrored is another kind of characteristic of a 1D random walk. And if you refer back to the lecture slides, you see a bunch of them where it's like they're all just the highest probability is kind of in the middle, and then everything else is kind of like off to the side here, right? And they all are kind of symmetrical, roughly symmetrical at least. But yeah, so we're all good for part A. Any other questions? Nope. Okay, well, if anything else pops up, just feel free to unmute your mic or type something in the chat. But for part B, it says now that given that there are 100 particles, how many do we expect to find a displacement of 20 micrometers? Or negative 20 micrometers, right? And that kind of, like I said, doesn't matter. Negative 20, positive 20, they're going to be the same probability. But in this case, they're specifically asking for negative 20 micrometers. So we know that like our probabilities, right? Or we can figure out like our the number of particles at a specific displacement by taking the number of particles and multiplying by our probability. Yep, exactly. So 100 times 0.06, we get 6 particles. But yeah. Or 200 particles. Yeah, if it's 200, then yeah, that's going to be a slightly different answer there. But it would just be double at that point, so 12 particles instead of 6. But yeah, that's part B. Part C now is asking us to determine the mean displacement of all 100 particles for or after this 20-second time interval. So this is just asking for your average, right? Determine the mean displacement. And so taking into account displacement, obviously we're going to make sure we input those negative values and positive values correctly. So if you remember when we're calculating the average, right, it's just kind of like the sum of this process, which is like your x value, and then multiplied by the probability of each x value, and then you add all those values up. So for example, we have negative 30 micrometers. That's a probability of 0.01. So we take negative 30 micrometers times 0.01, and then add that to negative 20 micrometers with a probability of 0.06. So negative 20 micrometers, probability of 0.06, right? And so on and so on and so on, right? So you keep doing that, and if you recognize the process, what's going on, right? So we know that these values are symmetric around 0. So if I take negative 30 times 0.01, and eventually I'll add it to positive 30 times 0.01. Well, those two will cancel out and become 0, right? And, if you kind of extrapolate that, you'll realize that at the end, your mean displacement is going to be 0 micrometers. Or you can know, obviously, that by the characteristics of a random walk, that your final, or your average, displacement is going to be back where you started, which is 0. So average x is 0 here. So if you go ahead and add all these up if you wanted to, just to show your work, which I highly recommend. I know it's tedious, but I would go ahead and, basically add all these values up, or you can just make sure to give an explanation as to why it's 0, because you have to show your work somehow. But I would recommend putting all the values there, because that's just a really easy way to show that you know what you're doing, and you can apply concepts from previous chapters and whatnot to get your answer, essentially. So I would recommend adding all these up. It's just a little bit better. And actually, give me one sec. Let me check too how they graded this question to make sure if they wanted you to add things up, or if they were all right just having an explanation of some sort. So let's see here. Oh, phenomenal. So when they graded ours, they gave us only 1 point for doing parts C through H. So parts C through H were just completion, it looks like. That's excellent, I guess. I don't know if it's going to be the same this year, but just solid recommendation from me. Add them up. But yeah, so part D now is asking us to determine the mean square displacement of all 100 particles after this 20-second time interval. So that's mean square displacement, right? And so that's just going to be the same. It's just now you're taking every one of those x values and squaring it, right? So remember when I said your mean squared with the exponent on the inside, it's just going to be x squared times your probability, right? So it's going to be the same adding up procedure, right? It's just taking every one of these values for the displacements and squaring them. So you have negative 30 squared times what? It was 0.01, right? And then we'll say positive 30 squared times 0.01. And make sure to put that like that. And then negative 20 squared times 0.06. Positive 20 squared times 0.06. And so on and so on. So if you do that, I don't know if you guys have gotten a chance to solve it yet, but does anyone have a answer for that? So 112. That's okay. So it looks like Leslie also got that. Anybody else get 112? And that'll just be, like I said, you take every displacement that you get, square it, multiply it by its respective probability. The units in this case would technically be micrometers squared, but yeah, because you're squaring, because this will be in micrometers, and so if you square that, it'll be micrometers squared, and then this is just technically a scalar value, so it doesn't really have any units. 0.01 is unitless, and so you'll end up with micrometers squared technically for your mean squared displacement. And that makes sense, right? Because then for part E, if they're asking for the root mean square, which is the XRMS, right? And that we know is equal to the square root of the mean square displacement. So if it's micrometers squared, when you take the square root, you should get micrometers. So that's kind of a sanity check there to make sure that you have the right value. And 112 micrometers squared is the correct values as far as I'm concerned. But yeah. Any questions at all about part D? Okay. And as I alluded to earlier, when you were talking about root mean square displacement, right? That's x RMS. RMS is root mean square. So then we're looking for, if we just look at our equation sheet, if you don't have the equations memorized, it'll be the mean square displacement, take the square root of that, right? So we already have that from before, which is the 112 micrometers squared. Take the square root, you should get around like 10.6 micrometers, I believe. Everyone else get that? All right, cool. Yeah, go ahead. So that would be your standard deviation, right? So that would be this. Yeah, that would be this one. That would be your standard dev. And if you think about it, right, your XRMS is actually equal to your standard deviation. Why? Because think about it. Your average final position is 0, right? So if this is 0 here, if I take 0 squared, well, that's 0. So my standard deviation is actually equal to just this part alone, the square root of the mean square displacement, right? Well, that's also XRMS. So if you remember in the lecture, they actually defined XRMS as being like the width of the distribution, which is the same thing as the standard dev because the two values happen to be equal. So if you have a greater root mean square displacement, you have a greater standard deviation. So therefore, if you look at like a bunch of graphs that have different like XRMSs, right, you'll realize that the one with the largest XRMS will have like the widest distribution. So it'll be like more spread out. So that's a little thing that I'm not sure if they went over, but just know that for your like 1D random walks, right, since your average final position is 0, well, 0 squared, that's 0, so it leaves you with a standard deviation being equal actually to your XRMS value, because XRMS is root of the mean square displacement, and so if your standard dev is equal to your square root of the mean square displacement minus your average final position squared, well, if this is 0, then you're left with your standard deviation equals square root of mean square displacement, which is also equal to XRMS. So XRMS is your width of your distribution. Make sense? Okay, awesome. Okay. So if there aren't any other questions about part E, part F is how does the root mean squared displacement compare with the standard deviation? So this is basically what I just said for part F. If you notice, if you write out, once again, actually, I don't feel like writing this out again. There. So if you take your mean square displacement, right, that's the 112 micrometers squared, and then subtract your average final position, which is 0 micrometers, and then square that, right, you should get root 112 micrometers squared, which is still 10.6 micrometers. So you notice that your standard dev is equal to your XRMS. So your XRMS is therefore then your value that you can refer to for describing the width of a distribution. So you can say that standard dev is equal to XRMS, and that's it for part F. No idea why they did this problem so weirdly and broke it up into like H parts. I think maybe just to like, I don't know, give people some confidence, I suppose. And if they do end up counting this one for actual points and not like for completion, then I suppose you can get some quality points from pretty decent difficulty problems. Yeah, H parts. But yeah. Otherwise, I mean, breaking it up into this many parts is also an excellent way to just to kind of get you to process each bit of information. Like the first two were just kind of review from the last chapter, and then you kind of get to here, which is more like, or F and G, where you kind of get into this week's stuff. So it kind of helps you ease into the new concepts, I guess. But that kind of brings us to part G, right? So we have determine the diffusion constant, right? The diffusion constant is just D, right? We're looking for that value. Well, how can we relate diffusion constant to whatever values we have now? So we know XRMS, right? So what equation could we use to relate diffusion constant to XRMS, for example? There we go. Yep. So XRMS, excellent job, is equal to root 2 dt, right? And so we know our XRMS, right? That was 10.6 micrometers. So to solve for our d, we just square that on both sides. We have 2 dt. We can divide over 2t, right? So then we have 10.6 micrometers squared over, or micrometers, sorry. I don't know why I said squared. Let me make this thing a little bit smaller. There we go. And then divide over 2 times the time, right? Which was 20 seconds. If you remember at the beginning of the problem, they kind of just hit that. Or in these parts right here, they said 20-second time interval, 20-second time interval. And it was here, 20 seconds later, right? So that's our time interval. And oh, I see what I did. Oh, my bad. So I meant not micrometers squared, like 10.6 micrometers, and then square that. That's what I meant. Sorry. Because we have to get rid of the square root. My mistake. And so if we do that, 10.6 squared divided by 2 times 20, what should we get for our diffusion constant? Yep, 2.8 micrometers squared per second. Those are your units because you have micrometers squared and over seconds here. So it'd be 2.8 micrometers squared per second. Any questions at all about part G? Nope. Okay. So, yeah, go ahead. So you're saying like for your for like 2D motion and 3D motion, right? So you're saying like, okay, so like for root, so 2D would be like 4 dt, and this would be 6 dt, right? So I don't think we can quite, yeah, go ahead. Yeah, if you wanted to, yeah, 100, yeah, like 112 just divided by 2 times 40, or 2 times 20, I mean. Yeah, you can do that. Yeah. Yeah, you can do that as well. That works. Because at that point, it would just be your mean square displacement alone divided by 2D, for example, to get your time. Or 2t to get your diffusion constant, whatever. But The reason why it gets a little bit iffy, I guess, for 2D and 3D, that's why I was kind of like, I was unsure if you could extrapolate, because once you get to like root 6 dt, right, this t isn't like the amount of time for it takes for like a molecule to move, for example, or a single molecule. It's more like, because at that point you have 3D motion, right? So you're kind of like moving, I suppose, like in a circle, and so you're kind of radiating outwards, right? X, Y, and Z directions as a molecule. And so at that point, if we had like a bunch of molecules somewhere like in the center, right, T would be the diffusion time, which is just like how much time would it take for a decent amount of the particles to kind of radiate outward to a specific position. And so for 3D especially, we don't call it XRMS anymore, we call it RRMS, as in like radius, right? Sort of. And so this diffusion time would just be like the amount of time it takes for a large percentage of the particles, right, that you have to radiate outwards to a specific position, right? RRMS. So just figured I'd clear that up, because that's also just a lecture concept as well. But we don't do too much with 3D motion. It's mostly just 1D stuff. Even rare kind of 4D, or 4D, 2D motion. I was thinking of root 4 dt. Yeah, if we had 4D, then that'd be weird. We had special effects and stuff. Yeah, RRMS deals with radius. XRMS deals with positions. VRMS speed. Yep. Yeah, RRMS is more just for the 3D motion stuff, because just think of it like a molecule, right? Just think of like a sphere or something. And so I guess it's just kind of the way we think about it is kind of radiating outwards, or radiating radius, right? It'll move in X, Y, Z direction. So I guess they just picked R because, I don't know, it's radiating and radius makes sense, as opposed to having like XRMS, YRMS, ZRMS or something. So X, Y, Z. So just take radius and that's it. But yeah, anyway. For part H now, they're asking us, or they're saying, at a later time, the probabilities that the particles' displacements are remeasured, though the new values are not given. Conceptually describe how the following quantities would change compared to the values from 20 seconds above. For example, they increase, decrease, or remain the same. So this is saying at a later time, right? So let's say 40 seconds, 60 seconds, 30 seconds, whatever. So you're increasing essentially the number of what? If I'm increasing like the time interval, right? In terms of diffusion terms, what am I increasing? Because we don't really call it time per se. It's not just time. What do we call it? Time step is, I mean, not rate, but yeah, time step is what we call it. So, and that's why like this t is, if you go back to the lectures or look at your equation sheet, it's not like a regular t that we see for like, yeah, it's the fancy t that looks like torque, kind of, tau, right? Fancy t. So that's your time step. So essentially, if I'm going from 20 seconds to 30, 40, 50, whatever, I'm increasing the time steps. So now it's just asking us what happens if I increase the time steps to each of these different variables here. So if I think about root mean square displacement, right? XRMS, root mean squared displacement, right? So what happens to that with time? Increase, right? So why do you want to explain why it increases? Okay, yeah, it's fine. No worries, no worries. Yeah. So increasing is absolutely right. Basically, we have to kind of differentiate between your XRMS and like your just your regular like average position. So when we talk about XRMS, this is a way of describing like the average distance away from the initial position, as opposed to like your average final position, right? So your average final position is like more or less going to be around 0, right? Won't always like be like exactly 0, might be a little bit off, but generally around the center 0, right? Or based on your like your starting position, right? So XRMS will describe the average distance away from the initial position. So as I increase my time interval, right, the particles are going to tend to move outward with time, right? So as the number of time steps increase, so as the time steps increase, my root mean square displacement will tend to increase as well. Oops, whoa. Right? And if I go ahead and relate it to the diffusion, right? So if I have x RMS is equal to root 2d t, right? So if I increase this variable right here, I'm going to be increasing my x RMS. So just generally though, like from a qualitative perspective, if you kind of think about the graph, right? So if I have, if I give the particles more time to move, essentially, they're going to move outward. Like if we were on a number line, right? This is 0, so like -2, +2, whatever. So I give them more time. Basically, they'll tend to move outward, farther away from the initial position over time. The average final position will still be around 0, right? Around the initial position, right? But the average distance away will tend to increase with time. So obviously, kind of think about it logically. If I give particles time to move, they're going to tend to move farther and farther away. Doesn't matter, like how fast they do it, it's just that they do, right? So if I give the particles more time to move, they'll tend to move outward. And so obviously, if we relate it back to variables, right, as the number of time steps increase, the root mean square displacement will tend to increase as well. And yeah, sorry for missing the chats earlier. So yeah, more displacements. So over more time intervals, the particle travels more, having more positions it can go to. Yeah, basically, as you increase the number of time steps, you're giving them more opportunity to move. So therefore, over time, they're going to tend to spread out more. Now, if we go to 2, location of the peak of the distribution. So if we were once again to think about this like with a bell curve, right, or with like the histograms that I was talking about before, right, location of the peak is the location with the highest probability of the particles being there, right? So how will that change? So we got decrease and we got same. Any other people want to chime in? So we got 2 sames, 1 decrease. Yeah, so it's always most likely around 0, right, or around your initial position. So location of the peak will remain the same with time, right? The particles will still most likely be found at around x equals 0, right? So with time, they're going to tend to spread out more, right? So maybe I have, oops, this is horribly drawn. So maybe my center here is at 0, right? And let's say this is after 40 seconds. Oops. Versus maybe this one right here was like, say, I don't know, something like that. This is maybe not too accurate, but you can see here that in either case, the peak is still at 0, right? It's just that now we can kind of relate this back to 1, right? Where if I increase the time step, so I go from 20 to 40 seconds, well, then my width of the distribution is going to be a little bit bigger, right? My root mean square displacement is going to be bigger, so I have, a greater average distance away from 0. However, my average final position will still remain the same around where I started, which is 0 meters or 0 micrometers, right? So location of the peak will tend to remain where we started, around 0 micrometers, right? So regardless of the number of time steps I have, right, I'm still going to end up, on average, most likely at my original position, which is at 0 micrometers. However, with time, like we said for part 1, the particles are going to tend to spread out. So like, let's say here, this is what I'm saying by this is like, okay, so this is 0, this is -1 micrometers, this is +1, and this is the same, right? But now here's like +2, +3, -2, -3. Those used to have no probability at all, right? So they used to be 0 probability that a particle would end up there after 20 seconds on average, right? But now there's a smaller probability, right? So they're kind of spread out more. They're able to reach a wider variety of positions, essentially. And that's what we're going to kind of get to. That's kind of alluding to part 3. But basically, as you increase the number of time steps, your XRMS will increase. So you're able to occupy like different positions, right? So your average distance away from your initial position will increase. And then at the same time, you know, you will still be most likely to end up at your original position. So here's the difference in peaks though, right? So maybe at first you had like, I don't know, 0.6 probability that you're going to end up at your initial position. Now you might have like 0.4 or something, right? Still the highest out of the bunch, but it might have decreased over time a little bit, right? Because the particles are now spreading out, so you can occupy more positions, right? And so regardless of the amount of time steps though, you're still going to have your initial position relatively be the greatest, or like the most likely position you'd end up. Thought it was asking for size, length of the peak, location on the Y. Oh, I see. Yeah, and you would be right. Like I was saying, right? So, this peak, right? It might decrease with time, right? Because obviously now you have like I said, the particles can occupy more positions. So, yeah, that individual peak by itself might decrease, but it's still, the peak is still at 0, right? It's like your highest probability is still at 0. I mean, here it might have been 0.6, and this might have been 0.4, but still 0.4 is like greater than 0.2 or 0.2 here or 0.1 here and 0.1 there, for example. So your initial position still will have the highest probability. Yep. Hopefully that made sense for everybody else as well. Any questions at all about part 2? Nope. Okay. All good. All right, awesome. Part 3 now is kind of what I was alluding to earlier, right? The width of distribution. So we already talked about this before, where the width of the distribution, which is what we normally define as a standard deviation, right, is equal to the XRMS, right? So it's equal to our root mean square displacement. So, well, if that increases over time, like we know from part 1, right, it only makes sense that the width will increase as well, right? And as Abigail put it, so width would increase as the particles have more time to displace farther. Yep. So if you give them more time to spread out, right, they're going to tend to spread out to different positions, right? And so that'll kind of spread out the width of the distribution, the width of the graph, right? So this is kind of looking at the 20-second for the 40-second one, right? So I'll give them more time. They're going to occupy different positions. So I have wider variety, right? Wider distribution, right? I have more positions that I can occupy. So the width of the distribution will increase. So if I increase time steps, it'll increase the XRMS, as we know from part 1. And then we know that XRMS happens to be equal to the standard dev, right? And that's, we kind of figured that out from part E. Because your average final position is 0, so 0 squared is 0, so your standard dev is equal to your XRMS. So if XRMS increases, then your width of the distribution will increase as well. So all good for problem 1? Okay, awesome. Problem 2. An amoeba is a single-celled organism, approximately spherical, with a diameter of about 500 micrometers across. An amoeba can ingest molecules by taking them in through the cell wall. And suppose an amoeba takes in a large quantity of sodium ions with a mass of 23 daltons, which is 23 grams per mole, and a radius of 100 picometers. While at a temperature of 310 Kelvin, the intracellular fluid of an amoeba has a viscosity of 1 millipascal seconds, similar to water. So now it's asking us, what is the RMS speed of the sodium ion? So what is VRMS? So that's a big question there, right? So anyone know the equation for VRMS by any chance? If you guys have your equation sheets pulled up. Yeah, so that's right. However, do we know the velocity here, right? Or the speed, do we have a value that we can refer to, kind of like we did for problem 1? Or is there a way we can relate temperature and mass and all that stuff, right? Well, that's right as well. I mean, for velocity, or for your RMS speed, I think you can use 6 dt. I think if you're moving in x and y direction, so, or x, y, and z, so yeah. But I believe that is something we'll get to a little bit later. And that's for XRMS, by the way, not VRMS. But Caroline is absolutely right. It'd be 3 kBt over m. So, I mean, we have values of like temperature and we can get mass, right, somehow. So we're just trying to figure out the RMS speed. So that diffusion constant equation could be used for the next part. Yeah, that's for part B. And that one is kind of, the one that you brought up is a little bit different. But that one, as you can see, doesn't really involve like the RMS speed particularly. But yeah, that's the one. This is the one that we're going to be using to figure out the RMS speed, because we know our Boltzmann's constant, we have our temperature, and we can figure out the mass pretty easily here. But yeah. And I actually don't have my equation sheet pulled up. I just remember a lot of these, and then let me see here. Let me actually pull this up here. So I want to make sure that I'm relaying the most accurate information with regard to the equations as well. So give me 1 second. Yeah. Okay, just making sure. This one right here, do we need to know this formula? I believe it's given to you. It should, at least. Yeah, okay, so I'm seeing that it doesn't look like it is given, but you can definitely rearrange it. It's not too bad. So we know that kinetic energy is equal to 3/2 kBt, right? And that's also equal to half mv squared. So if I just want to solve for the v, right, well, then I can just set these two equal to each other, right? So half mv squared is equal to 3/2 kBt, right? I can multiply over the 2, divide by the m, right? So if I multiply over the 2, well, the 2's here, if I multiply by 2, the 2's will cancel. So I'm left with 3 kBt. And if I divide by m, I'll be left with v squared. So if I take the square root, so VRMS is equal to root 3 kBt over m. So you can kind of derive it that way as well. But yeah, maybe I guess they didn't give you this one out of the box. So, oh, it is given. Maybe I overlooked it. Energy section. I don't know. The equation sheet I'm looking at, I don't see it. Or maybe I'm just blind. I don't know. Yeah, I don't see this one, like this overall one, but I see these two. But yeah, you have to rearrange it, honestly, yeah. But this one would be a good one to remember, I'd say. But it's not too bad. And if you forget it, you can just kind of rearrange it this way. But yeah, so for VRMS, root 3 kBt over m. Well, actually, you know what? I'll solve for mass because that's the only unknown that we have, because we know temperature is 310 Kelvin. So we weren't directly given the mass, but what do we have? If you have that it's 23 Daltons, it's 23 grams per mole, right? We have the molar mass technically. So how can we get to just grams? Yeah, exactly. Convert mass using Avogadro's, right? So 23 grams per mole times 1 mole over 6.022 times 10 to the 23. We can say like particles, right? Or molecules or whatever. So that'll give us what for our mass there? Oh, and then also, don't forget that this will give you a value in grams, right? But what are the SI units? Yeah, there you go. Divide by 1,000. Excellent. Yeah. Because you have to go from grams to kilograms, right? So if you just divide by 1,000 grams, that should give you kilograms on top, because your SI unit should be in kilograms. So 1,000 grams, 1 kilogram, and Abigail got 3.82 times 10 to the negative 26. I got the same. That's kilograms, right? And that's like kilograms per particle, essentially. And so we can kind of plug that back in here. 3 times RKB, which is 1.38 times 10 to the negative 23 joules per Kelvin, times 300 ton Kelvin. Oops. Divided by our mass here, which is 3.82 times 10 to the negative 26 kilograms, right? And so that gives us an RMS speed of, yeah, particles, molecules is just kind of relative to what was said in the, yeah, this one said molecules, so sorry, molecules, particles, doesn't really matter. Just kind of depends on what they said in the problem, so that, yeah, it should be particles, or molecules, sorry. I'm off my game today. Yeah, I'm hungry, I'm thirsty. Yeah, how many hours left? We got 2 hours. We're good. All right. So for our RMS, I got 579.68. Yeah, 579.7 meters per second. But yeah, that should be your RMS speed. And like I said, you kind of figure that out by relating whatever values you have existing, right? So I know I have temperature. I know they gave me some kind of molar mass, right? So, well, if they're looking for RMS speed, I mean, you can kind of cycle the equations if you want to. I mean, you think about it, RMS is equal to mean squared speed, I guess. But we don't really have a speed to begin with to square it and find the square root of it to get the VRMS, right? So how can we even get some kind of, speed or velocity value or whatever we kind of have to think about the included information given to us, right? So I can kind of use this equation, which is derived from setting these two equations equal to each other, to find out my VRMS. Makes sense for part A? $570. Might just depend on how you round it for your mass. Or you might have plugged in a wrong value. It should be, maybe I was a little unclear here, negative 26, maybe, I don't know, if you saw it like negative 24 or something like that, but yeah. You got 570, 579, I mean, that'll probably just be some rounding issue, or might have plugged in something wrong here or there. Or I could have done something wrong, so let me check it. It'd be funny if I got something wrong and they never caught it. Ah, so you put in 300. I got you. No worries. No worries. Yeah. But yeah, that's part A. If there aren't any other questions about part A, we can move on to part B. So part B is now asking us to figure out the diffusion constant, right? Looking for the diffusion constant. Someone mentioned the equation earlier, right? So they gave us viscosity, we know our temperature, we know a lot of different other things, right? So yeah, diffusion constant kBt over 6 pi times our viscosity times r, right? Our radius there. So we can kind of just plug and chug, honestly, because we have 1.38 times 10 to the negative 23 joules per Kelvin. You'll get really good at memorizing this value if you ever forget it, like physics 2, first 4 weeks. Oh, that's just like trauma memory right there. So yeah, temperature is 310 Kelvin. I love how I like throw out like things and then it's just, I just move on normally with the problem. I'm like, yeah, physics 2 is hell, and then continue with the problem. But okay, yeah, 6 pi times our viscosity, which is the 1 millipascal seconds, right? Which we can just divide by 1,000 to get that in Pascal seconds, right? Which is our SI units. So 0.001 Pascal seconds, and then multiplied by our radius, and they gave us our radius, which was 100 picometers. I believe, yeah, right? Yeah. So 100 picometers, we can convert that to just meters, right? Again, to get the SI units, right? So 100 picometers would be equal to, I think, 1 times 10 to the negative 10 meters. Yeah, I think so, if I'm not mistaken. Let me check it real quick. Yeah. So this is 1 times 10 to the negative 10 meters. And so that we should get our diffusion constant to be what? And if anyone's unsure about how I got this, please let me know, and I can kind of explain it real quick. Yeah, it's picometers. Picometers, which is, I got really good at memorizing this as I don't know, you just do a lot of conversions in physics too as well. So you have deci, centi, milli, micro, nano, pico. So deci, centi, milli, micro, nano, pico, right? So this is 10 to the -1. No, I just mean that 100 picometers is equal to 1 times 10 to the -10 meters, but 1 picometer is equal to 10 to the -12. Yeah, so it goes deci, centi, milli, micro, nano, pico, 10 to the -1, -2, -3, 6, 9, 12. So 100 picometers multiplied by 1 picometer is 1 times 10 to the -12 meters, right? If I multiply those two together, I should get 1 times 10 to the -10 meters. And Christian got 2.27 times 10 to the -9. Yep, and it's meters squared per second. Let me move this so it's a little bit clearer. There we go. But yep. Meters squared per second. And I guess, I don't know if anyone wants to bother with like trying to memorize these, but it helps, I suppose. But your deci and your centi, or deci, centi, milli right here will just be 1, 2, 3, right? Anything after that will increase in 3 increments, right? So 3, 6, 9, 12. 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12, right? And then, I don't know really how you're supposed to memorize these, but I just kept repeating them in my head. And they're actually in alphabetical order, sort of, except for the D and the C. But deci, centi, milli, micro, nano, pico. There's bound to be some acronym out there, like MCAT acronym, that people have come up with to remember this. It's probably really funny, I just don't know it. Not yet, at least. Anyway, yeah, we could try, but I don't know if I could come up with something on the fly. I'm not good with acronyms. Actually, yeah, no, I'm not good with acronyms. I'm just good at memorizing. Like, I don't know. Let me look it up. Memorize SI prefixes, acronyms. I don't know, why would you even need an acronym to memorize these, honestly? Like, that you'd spend time figuring out the acronym and then yeah. So I got one here. I just looked it up. I was actually gonna pull that up right now. So you're on the right track. Apparently, it's the great man King Henry's daughter Beth drinks cold milk until 9 p.m. Okay. I think I would spend more time memorizing that than memorizing like their values here. But sure. You know what? I will drop the link in case anyone wants to look at that. But they start out from like tera, giga, mega, kilo, and all that. So here's that link. If you guys want to look at the mnemonic there. That's a funny one though. But anyway, part C is asking us how long would it take for a large number of sodium ions to diffuse inside the amoeba so that their RMS displacement is 500 micrometers. So here's the key here, because if they try to trick you with a multiple choice question or something, or even, I doubt they would do this for a written response because it's just so easy, but I could see this for a multiple choice. So if they said, how long would it take for a sodium ion to diffuse, right? Just one. There's no answer to that. You can't figure that out because all of this stuff is relative, like just averages, right? So I can only figure out the average distance away from the initial position. I can only figure out the average, like final position. I can only figure out the average time, right, that it would take for all these particles to diffuse a certain distance, right? But if they ask me for a specific, like if they just said how long would it take for one sodium ion to diffuse, I can't figure that out. So that would be like no answer or need more information or something like that, or you can't figure it out. I don't know if they pull like a multiple choice question like that. But yeah, that's that you can't figure that out because everything that we do here is with averages. So I can figure out average distance, average time, all that, but I can't figure out like an exact number. And so that's why they say a large number of sodium ions, right? So that kind of allows you to solve the problem. So they're looking for time here, right, for a large number of these sodium ions, and the XRMS is, well, it wouldn't be XRMS in this case because it's a molecule, so we're traveling in 3D, right? So it would be RRMS, right? And that's 500 micrometers. So what is the equation for RRMS? Yep, square root 6dt. So we have our 500 micrometers, right, which is just 500 times 10 to the negative 6 meters, is equal to, or we can go ahead and square that already, so we can get rid of the square root, right? And then divide that by 6 times the diffusion constant, which is 2.27 times 10 to the negative 9 meters squared per second, right? And that should give us our time. So what should we get for our time here? $18.4. Yeah, that's about what I got. 18.36, 18.4 seconds for a large number, once again, large number of ions to diffuse. You know, like I said, you can't say one sodium ion, like you can't figure out the time for one of them to diffuse because we're just looking at averages, right? So if everyone's good for part C, we can move on to part D. Now, yeah, go ahead. Yeah, so it's in micrometers, right? So it would be, if I wanted to convert that to meters, I do 500 micrometers times 1 micrometer is 1 times 10 to the negative 6 meters, right? So, yeah. So 500 times 10 to the negative 6 meters. Or alternatively, you can say 5 times 10 to the negative 4 meters as well. So just move it over 2 decimal places. Yeah, so 500 times 10 to the negative 6 is 10 to the negative 6 meters is the same as 5 times 10 to the negative 4 meters. Same thing. But yeah, can then move on to part D. So now it's asking us if an individual sodium ion was moving in a straight line with a constant speed equal to its RMS speed, right? So how long would it take to make it across the amoeba, which is 500 micrometers? And explain why this number is different from the time you computed in part C. Well, first of all, they're asking us to just move in a straight line, right? What's different about part D and part C just from that little thing right here? That the fact that it's moving in a straight line. Does this indicate anything? Ring any bells? Exactly, right? So they're moving in random motion, and if you look at the equation here, well, that's 3D motion, right? So it moves in X, Y, Z. It's bouncing all over the place, right? But now they're just asking for it to move in a straight line, which is just 1D motion, right? That's just going to be in the X direction, for example, right? And so basically, they're saying that whatever VRMS we have that we got before, right? Then that's all of a sudden going to be equal to the speed that we want it to travel in this straight line now, right? So they're also asking us basically to find out how long it would take to make it across 500 micrometers, right? Well, basically, what does speed equal, right? What is the definition of speed? Yeah, right? I mean, yeah, meters per second, distance over time, right? So, yeah, I can say like meters per second, or, displacement over time, right? So this X right here, for my VRMS, right, that's going to be what value specifically? This delta X right here, so the distance that I traveled. Yeah, exactly. So 500 micrometers, which is the 500 times 10 to the negative 6 meters, right? Divided by some time that I don't know, and is equal to what? VRMS, right? Because that's what they kind of determined earlier. So if that's equal to VRMS, if we just go back to part A, we know that VRMS is 579.7, right? So this is equal to 579.7 meters per second. So then we can just solve for time, right? Multiply over t and then divide over the 579.7. So that should give us delta t of what? Yeah, I got closer to 8.6 times 10 to the negative 7 seconds. Yeah, I would check your values again. Maybe you threw in like a different exponent or something that might have thrown things off. Or typed in your speed wrong or something like that. But it should be around 8.6 times 10 to the negative 7 seconds, right? That's to travel 500 micrometers, that's a lot faster than 18.4 seconds, right? So to explain why it's different, kind of already did that earlier, right? But just pretty simple explanation, actually. I mean, here they're wanting us to move just in a straight line, right? And then basically in part C and every part before that, what they're saying is that the molecules are moving in this random motion, right, in 3D, right? So when they're moving in 3D and moving in multiple directions, right, they're constantly bouncing off other molecules, constantly changing their direction, constantly in collisions, right, completely randomly. So That's why this time is a lot different, because you're only moving in one single straight direction. You aren't, having as many collisions. You aren't bouncing around in other directions as much. So it'll take a lot less time for you to cover that same amount of distance, because you're not as obstructed by all the other molecules that you would be coming into contact if you would have moved randomly. Do I peer lead 132? Well, not at the moment, but I do plan on doing that next semester as well. So if all of you guys are taking 132 next semester, then I'll probably see you next year. Or not next year, well, you know what I mean, next school year. So, I can't promise like 100% that I'll be, I guess, as good as you guys see me for 131, because I think I still have a lot of flaws, but 132 is I mean, like, I have to work really hard for 132, but I don't know. I kind of feel like the work is a little bit less, because a lot of the online homework next year has there's not a lot of written. It's just a lot of multiple choice for the online homework for 132, and the written homework I feel is generally a bit simpler than 131. It's not unlimited tries, right? It's only 5 attempts, unfortunately, but 5 I think is more than plenty to do well. I don't think many students do like bad on the online homework, and then I'm gonna be honest, like, I'm kind of against this in a way, but students end up like sharing the answers anyway, like the night before the homework is due. So you'll always get that one person that'll just like send out all the online homework answers. So are there drops? Yeah, there are drops. They drop one quiz, I think, and one online homework or something like that, but that's bound to change. It almost always, they threaten us with one only for each thing, and then they end up changing it. I feel that's how they did for 131. They ended up dropping like 2 quizzes and 2 homeworks and something, and then they dropped the curve as well. So there's always hope, but yeah, 132 is totally different than 131. You don't use like most of the concepts you learn now, because yeah. Oh yeah, absolutely. Yeah, and in fact, I feel like the formula sheets for 132 are more helpful, because they also like kind of give you concepts, like for example, okay, so I'm gonna go off on a little bit of a tangent, but we're doing like circuits right now, capacitor circuits, electricity, all that. So for our last quiz, I remember everyone at my table, we were doing like a really simple, just adding up resistors in series and parallel, right? And so what ended up happening is that obviously there's 2 ways you for series and parallel, you add up the resistors in different ways. You either take the reciprocal of the resistors, or you just simply add them up. And so it just gets kind of confusing, because adding up resistors is a little bit different than adding up capacitors. And so anyway, make a long story short, the circuit was in series, and people just did the equation for the parallel circuit instead of a series. And so I caught my mistake with like 2 seconds left, or not 2 seconds left, 2 minutes left on the clock, because I just realized, I was like, the rest of this problem is not working out. I don't know how everyone else did it, but series is not right, or parallel is not right. The way I was adding it up in parallel was not right, and so I ended up changing my answer last minute, and I fixed it. But the only way I could have gotten it, to be honest, was the fact that the equation sheet, luckily, like at the very bottom, like had a little asterisk that said, this is how to calculate series and how to calculate parallel, and they explained like why and stuff. Like there's like little explanations or little like clarifications that you have on the equation sheets that are helpful to kind of help you remember what is what, especially when you get to like a little bit more confusing concepts. So yeah, I generally feel that formula sheets for physics 2 are really helpful. But yeah, it's just, I feel like 132 is less work. It's just the concepts are a little bit more difficult to wrap your head around. Yeah. Yeah. Series from Calc 2. Yeah. Taylor series are a whole different thing. I hate those boys. Screams Taylor series, yeah. I don't like them at all. I was good at them, but I did not like them. I did not enjoy. Thankfully, on the AP Calc exam, AP Calc 2, that is, there's no Taylor series to be found. Actually, there was F parts on our exam, and only the last part was asking about Taylor series. Everything else before that was Calc 1. So, yeah. Anyway, sorry for going on a tangent. That's problem 2. Any questions at all about problem 2? Nope. Alrighty. So then we can move on to problem 3. I don't like this concept either. I don't like flux. I just don't like the variable j. It just looks like a weird variable to use in physics. Everything else makes sense. J just looks out of place. I don't like it. Yeah, I kind of went over the how it was different, but I can go over it again real quick. So let me just actually, write it down this time instead of just kind of like verbally saying it. But yeah, no worries. So basically, you know what? Let me actually just type it out because I don't know. I feel like I want to type right now. So let me make the font a little bit smaller. So basically, in this case, sodium ions are moving in a straight line and aren't moving in 3D as before. So they're bumping into fewer molecules, less collisions, and they aren't constantly changing directions, basically. So the fact that they aren't so affected by bumping into each other and colliding, right, makes it much quicker to reach 500 micrometers, right, in less time. So basically, just because there aren't as many collisions, right, because you're only moving in one straight line direction, you're moving in 1D motion, right, as opposed to 3D motion, you're moving X, Y, Z, so you're bumping into a lot of different molecules, you're moving in random directions, right? So it's just like, imagine moving, I don't know, literally just like 20 feet or something in a crowd versus just like, walking 20 feet normally without anybody in front of you. If you're in a crowd, everyone's just going to be bumping into you, so it'll take you like maybe, 20 seconds to get there, as opposed to like maybe, 10 seconds or something, or 5 seconds to move there otherwise, So it's just a matter of like traffic and no traffic. Yeah, exactly, traffic and no traffic. But yeah, this is a little bit more kind of like a formal way to kind of say that, but yeah, I ended up losing points on this question because I actually forgot to explain, so there's my redemption for the day. Anyway, Caroline, did that make sense? Make sense? I said made sense. My tenses are all like messed up today. Yeah. Wait, was I? Yeah, no, hold up. Yeah, Caroline was the one who asked that, right? I'm just making sure. Because I saw the chat and then it's not there anymore, I guess. I don't know. If I'm just... Are you serious? That was Christian? Wow. I read that as Caroline for no reason, good reason at all. Oh my gosh. Okay, I'm hallucinating. I'm sorry. Yo. Yo, no, wow, that's a first. No, I completely saw that. Wow, okay. Okay, okay, move on. Move on. It's good at least that I like, yeah, at least I messed up a name and not like a whole problem. Like, if I was just tripping on my numbers, then okay. Whew, okay. Alright. Problem three. She must have like Caroline, you must have like been like, what the heck is this guy talking about? Wow. Okay. Um so Common three potassium channels, cell membranes contain potassium channels which can open to allow potassium ions to flow into and out of cells. These channels are approximately cylindrical with a length of 4 nanometers and a diameter of 0.5 nanometers. Consider a cell which has a concentration of potassium ions at 100 millimolars inside the cell and 5 millimoles outside. When its potassium channel opens, it allows ions to flow out at a net rate of 10 to the 8th ions per second. Okay, alright. I can't focus anymore. What is the flux of potassium ions when the channel is open? Use the usual coordinates with positive x to the right from inside to outside and give your answer in units of ions per meter squared seconds. Okay, so they're asking for flux, right? Well, I know that flux times my area is equal to what? So change C over change in x. Well, that's going to be one of the equations, but I was thinking just like with the area. So flux times area, and that's equal to the delta n over delta t. Yep. So this will essentially be like ions or particles or molecules per second or whatever, right? So in this case, they kind of gave us that already. And so this is just equal to 10 to the 8th ions per second, right? And we need to figure out our flux, so only other thing left to figure out is the area, right? So how can we get our area? And by the way, that's not the area of, like, think of it here. So this is a cylinder, right? So would we find the area of a cylinder, or would we find an area of a circle? Oh, this is really important. Circle, right? So why is that? Why do we got to figure out an area of a circle when they clearly said just, they just gave us a cylinder, right? Why is it just a circle that we got to figure out? So if we were to figure out the area of a cylinder, that would be like surface area, right? So the reason why we don't figure out the surface area of a cylinder in this case, right, which we can do, is that for flux, you're not looking at, like, I guess, traveling along that whole channel. It's just the flow and that cross-sectional area, right? And so the cross-sectional area of a cylinder is a circle. So we're just looking like the particles just entering that cross-sectional area. So it's just the entrance, not like the whole path or anything like that. So we're just looking for the area of a circle. So we know that our radius is, well, our diameter is 0.5 nanometers, right? So our radius should be 0.25 nanometers, right? And we can square that and figure out our area. I got around 0.196 nanometers squared, right? And then I can convert that to meters squared by doing like 0.196 nanometers squared. And I know that in 1 nanometer, there's 10 to the negative 9 meters. And then I can go ahead and square this whole thing because I have to have nanometers squared and then meters squared, right? And so that should just give me 1.96 times 10 to the negative 19 meters squared, I believe, right? And so that'll be my area. And then I can kind of divide my area over here to get my flux. So my flux should be equal to my rate here, right? Divided by my area. So this was 10 to the 8th ions per second divided by 1.6 times 10 to the negative 19 meters squared. Right? And let me check that real quick, make sure everything is in order and kind of makes sense. Yep. So what did you guys get for our flux here? Yep, we got about the same. I rounded to 5.1 times 10 to the 20 times 10 to the 26. And that's ions per meter squared seconds, right? Or seconds meter squared, whatever. Yeah, go ahead. So the delta n over delta t is just this whole value here, 10 to the 8th ions per second, because your delta n is like your molecules, ions, or whatever, right? So, and then delta t is your time. So this is already n over delta t, or delta n over delta t, right? So this whole thing becomes 10 to the 8th, and then we can divide it by the area to get our flux. Yeah, with net flow of ions. Any other questions about part A? Mope. Mope is a word, right? Yeah, mope is like crying or something like that. Yeah, being sad, moping. Ah, it's a fitting word. It's a fitting word for the situation at hand. But if there aren't any other questions about part A, we can move on to part B. So yeah, part B is we need to figure out the diffusion constant now, right? So we're looking for diffusion constant. Are the potassium ions moving through the channel in units of micrometer squared per second, right? So we can kind of relate this to the flux value that we had before and our second equation for flux, which someone mentioned earlier, was our negative of our diffusion constant, right, times our delta concentration over delta x, right? So, all right. We know that our... What was I going to say next? I totally lost my train of thought. Yeah, shoot, I don't remember. Okay, so let's just start with rearranging the equation first. So we have our flux times delta x over delta c is equal to negative of our diffusion constant, right? So we can figure out our delta c though by looking at the concentrations that we have here. So we have 100 millimolar inside the cell and then 5 millimolar outside, right? So we can kind of figure that out, our delta C, right, by just subtracting 100 minus 5, right? So that'll give us 95 millimolars as our delta C, right? And so we can convert that as well to moles, and then from moles to meters cubed, right? So we can get our SI units. So 95 millimoles, that'll just be 1,000 moles in 1 mole. In 1 mole, that is, yeah. Let me move this over a little bit. And then, not mole, sorry, in 1 molar, my bad. And then molar is moles per liter, right? So let me actually, you know what, I'll just do this in 2 pieces. So first we'll convert to moles, right? So that'll give us 0.095 molar. And so 0.095 molar is moles per liter. And then we can convert to meters cubed, right? Because we know 1,000 liters is 1 meter cubed. And so then that should be equal to 95 moles per meter cubed, right? So we can have our SI units there for our delta C, right? So we have our delta C, right, which is the 95 moles per meter cubed. And then we can also get rid of the moles and convert that to like the ions, right, just by multiplying by Avogadro's number. So we can do 1 mole times Avogadro's number to get the number of ions per meter cubed, that is, right? So that's one thing. And then once we have our ions per meter cubed, then we're looking at plugging all this stuff in. So we have our flux from before, which is 5.1 times 10 to the 26th ions per meter squared seconds, right? Then we can multiply that by our delta x, which was the length, right? The 4 nanometers there. 4 times 10 to the negative 9 meters, right? And then divided by our delta C, which, like we said before, is just going to be the 95 moles per meter cubed times Avogadro's number to get it in ions per meter cubed, right? So the ions eventually kind of cancel out there. So it'll just be 95 basically times 6.022 times 10 to the 23rd. And so that should give us a diffusion constant of what? And this should be in meters squared per second initially, and then we'll convert it back to micrometers squared per second. And I forgot one thing, actually. I should edit this a little bit. So for our delta C, this is equal to out minus in, and so that'd actually be negative 95. So that's my mistake, because it should be outside minus inside. So C is C out minus C in, right? And so that's gonna be 5 millimolar minus 90 or 100 millimolar, sorry. And so that's going to be negative 95 millimolar. My bad. But yeah. For the diffusion constant, that was earlier. Oh, that 5.1 times 10 to the 26? Yeah, so eventually I should be like, well, it shouldn't be the negative of that because you already have a negative d here, right? So the negatives will cancel out because I just made a mistake here. So if I plug in a negative here, right, the negatives will cancel out. So your diffusion constant should end up being positive. But I don't think I got 5.1 times 10 to the 26. Or is that from earlier? Yeah, that's that's about right. 3 point. I got specifically. I think I got 3.56 times 10 to the negative 8. And that's meters squared per second. But then they want it to be in micrometers squared per second, right? So then we have to convert that. So, if we convert that, so meters squared, right? So I want to convert that. Let me put this here, 3.56 times 10 to the negative 8 meters squared seconds, right? Then I know, so I believe you should get, yeah. Did I miss it? Yeah, no, I forgot to square it. That's what I forgot to do. I felt like something was off. So 1 second here, let me kind of adjust that real quick. 3.56 times 10 to the negative 8. And then multiplied by that squared. So you should get around 3.56 times 10 to the 4th micrometers squared per second. So if you would have just divided by 10 to the negative 6, you would get 0.0357 or 356 or whatever. But you have to square them because it's meters squared per second, and then you need to do micrometers squared, right? So you have to square that whole thing. Does that make sense? So you're careful with the conversions from meters squared to micrometers squared or vice versa. You have to square like your conversion factor. So if I'm doing 1 micrometer is equal to 10 to the negative 6 meters, right? So when I do that, I have to put a parentheses and then square it to get micrometers squared, for example. But yeah. Any questions about part B? Yeah, we only want the answer in micrometers squared per second. Yeah. Obviously, you're going to get meters squared per second somewhere along the line, but just make sure to circle this as your final answer. The one in micrometers squared per second. There we go. Yeah, so don't circle the other answer because that one's incomplete. Because that's just meters squared per second. So then wait till you convert it and then circle that as your final answer. But yeah. All right. Any other questions about part B? All right. I'm gonna take that as a no, but if anybody else has any questions, just feel free to let me know. If the cell is at a body temperature 310 Kelvin and the radius of potassium ions is 1.33 angstroms, what is the viscosity of the fluid the potassium is diffusing through? So we need to figure out viscosity. They gave us some radius, they gave us temperature, right? Well, how can we kind of get viscosity? Viscosity is kind of out there, right? We've been doing flux and diffusion and whatever, right? So how can we get viscosity? Yeah, so there's a diffusion formula, right? That'll do, we used it before actually, kBt divided by 6 pi times viscosity times radius, right? So we have our diffusion constant from part B, right? And then we can just kind of plug and chug basically to figure out our viscosity, right? So our viscosity, if we kind of rearrange things, right, it'll be what? kBt divided by 6 pi rd, basically. So you can plug things in, right? 1.38 times 10 to the negative 23 joules per Kelvin times our temperature, 310 Kelvin, right? Divided by 6 pi times our radius. And that was 1.33 angstroms, which is times 10 to the negative 10, I believe. Yeah. And then multiply that by our diffusion constant, which was what from before, 3.56 times 10 to the, oh, but here's the thing though. Don't use this one because this is in micrometers squared per second, right? Everything else is in meters, SI units, right? So I would use this one, 3.56 times 10 to the negative 8 meters squared per second. So make sure for this one you use your SI units again to get your viscosity. Yeah, convert to meters. So what should you get for your viscosity there? Four point eight, yeah. I got 4.7, but just rounding at that point. But yeah, I can do 4.8, I think, times 10 to the negative 5, and that's Pascal seconds, right? Because we're doing SI units, so Pascal seconds for viscosity. Yeah, 4.8. So that's the gist of this written homework. What time is it? We have 5 minutes left. Anybody else have any other questions about the written homework or otherwise? I think Isley, you said you wanted to ask questions about the online. I'm not sure if we would have time to answer all those questions, but if you want to, you can just send me a DM with like the problems that you're a little unsure about, and I can kind of look at them, and I guess like send explanations or whatever. The last answer was 4.8 times 10 to the negative 5 Pascal seconds. And this should be on YouTube and Google Drive, yeah. I'll try my best to upload them in as fast as I can, I guess, because I don't know, my computer sometimes like will shut off and interrupt the uploading process. So hopefully it doesn't do that this time. But yeah. That's it. Yep, no problem. Hope you guys have an awesome rest of your day too. Yeah, absolutely. You too.